Last week, when we talked about the electrons in an atom, we talked about how the electrons are found in different energy levels. And if you give an electron some energy, either through heat or through electricity, that electron will jump to a higher energy level. And then as it loses that energy, it falls back down, and that energy comes out in the form of light. And the light is different colors based on the amount of energy that's lost. So each color has its own wavelength and its own frequency. And we talked about how that's connected to the use of fireworks. Different elements produce different colors. When you give them energy, and the electrons then fall back down to the energy level they started in and release that energy as light. What we're doing today is learning a little bit more about where those electrons are located, and we're going to try to put an address on each electron in the atom so we know where they are. And we'll try to describe a few different pieces of information for this address, just like if you were putting an address on an envelope, you would have to have a few different pieces of information for that address on the envelope as well. So keep that in mind as we go through the notes. That's our big idea for today, trying to put an address on the electrons. We're going to start with a little bit of history on the study of quantum mechanics. Remember, that's how electrons are organized, or how energy levels are organized. The scientist who is credited with coming up with the study of quantum mechanics, his name is Werner Heisenberg. He was German. And this time frame was right about 1925 or so in between the two world wars. And he's considered to be the father of quantum mechanics. Again, quantum mechanics is where are the electrons, how are they organized, how is the atom put together. And at that time, Werner Heisenberg was the leader of the German nuclear fission research, and again, this was in 1925. And he is most famous for coming up with one principle or one idea that has to do with the study of electrons, and it's called the Heisenberg uncertainty principle. Uncertainty means something that we don't know for sure, so something that we're not sure about. The Heisenberg uncertainty principle says, the more precisely the position is determined, the less precisely the momentum or velocity is known. When we're talking about electrons, we know that electrons are always in motion in the atom. We're taught that when we're first taught the idea of the atom being kind of like the solar system, with the nucleus in the center and the electrons going around it in rings around the outside. So we know that electrons are always in motion, so they must have a momentum or a velocity. And then they also have to have a position or a location as they move. But if you wanted to pinpoint the location and know exactly where the electron was, you would basically have to stop its motion. Because as long as it's moving, its location is constantly changing. So the more precisely the position is determined, the more precisely you know the location, the less precisely you know how fast it was going. If you want to pinpoint the location, you pretty much have to stop the electron. So then you wouldn't know how fast it was going. Here it is written out in a little more plain English. It's impossible to know exactly where the electron is and how fast it is moving at the same time. One or the other. You can't have both at the same time, because if you want to know the velocity, it's got to be moving. And if you want to know the location, you have to stop it. A comparison for this, on a little more visual level, is the blades of a fan. When you turn the fan on, especially if it's on high speed, the blades all tend to blur together, and you can't see where each individual blade is. If you want to know where each blade is, you have to stop the fan, but then it's no longer moving. So that's the Heisenberg uncertainty principle. We can't know both things about the electron at the same time. We can't have a precise location and a precise speed at the same time. The next idea that we need to talk about is how then can we describe this location? If we can't get a precise location, what can we get? And what we can get is an area or an approximation of where we think those electrons are. And this was first come up with by Erwin Schrodinger. We've talked about him before. We did just a little bit about his work in our History of the Atom Day. And on that day we talked about how he liked to use math equations to describe where electrons are. And so he's pretty famous for this one equation that he came up with called the Schrodinger Equation, which describes where the electrons are in an atom. And it's kind of like the idea of in algebra, how you can use the equation of a line to tell you where that line is on a graph. It's kind of that same idea. He uses an equation to describe where the electrons are located in the atom. But like we said, we can't have an exact location because electrons are always moving. So what this equation does is it finds the probability or the odds that an electron may be somewhere. So what are the odds that we're going to find an electron at that spot? So we have an equation that can approximate where they are, find the odds to where an electron is going to be, and we know that we can't pinpoint that location because the electrons are always moving. So, where are they? How do we describe where they are? There are 3 levels of organization, and by that I mean there are 3 pieces of information. Now if you think about comparing this to an envelope that you're going to put in the mail, think about the information you have to have on that envelope. Usually the top line of the address is the name. Then, after that, on the middle line, you have to have a house number and a street name. And then on the third line, you have to have the town and the state and the zip code. We're going to simplify that a little bit and keep the 3 main pieces of information from that address. So for our addresses, or for our purposes, we're going to compare the addresses of the electrons to having a town, a street name, and a house number. The first level of organization is called the principal energy level. These are the same energy levels that we talked about last week. And this would be compared to having the name of a town or the name of a city on your envelope that you're going to put in the mail. This is kind of like the big picture. It's the general location. Where is that envelope headed to, or where are those electrons found? Principal energy levels tell you how close the electrons are to the nucleus, and to differentiate between them, we just use numbers. Energy level 1, energy level 2, energy level 3, and so on. 1 is closest to the nucleus, 7 is furthest away. The next level of organization is called a sublevel. That prefix sub usually means below or within, so sublevels are within energy levels. And this would be compared to having a street name on your envelope. This is the next most specific piece of information that you need. First came the town, the big idea, then comes the street name. Street names are like sublevels. The sublevels tell you the type or the shape of the electron cloud. Electron clouds are areas where the electrons are found, and there are 4 different types, and each type has a different shape. We'll go over the shapes in detail a little bit later, but since we already used numbers to label the different energy levels, now we have to use something different for the sublevels, so we use letters. And the 4 types of sublevels are S, P, D, and F. And as far as I know, those are completely random letters. They don't stand for anything. Maybe they weren't being used by any other quantities. So S, P, D, and F. And where you find these street names is a little bit interesting. In the first principal energy level, and that's what this PEL stands for, principal energy level, we only have one type of sublevel, and that's the S. So if you're using the envelope address comparison, in the first town we have S Street, and that's it. There are no other streets in the first town. There are no other sublevels in the first energy level. In the second principal energy level, we have an S sublevel and a P sublevel. So again, with the comparison to the towns, in the second town we have S Street and P Street. In the third principal energy level, we have S, P, and D. And you might be able to predict at this point, in the fourth principal energy level, we have S, P, D, and F. And we'll continue to have all four types of sublevels for energy levels 5, 6, and 7. There are more letters beyond letter F, but we're not going to learn what they are. We're stopping with letter F. Next, we need a house number. So, within a sublevel, there are a certain number of atomic orbitals, and orbitals are like electron houses. These are where the electrons are found. There's a certain number of each type of orbital per energy level, and that goes along with what type of sublevel it is. So the S sublevel has one orbital. If you're keeping up with the envelope comparison, S Street has one house. P Street has 3 houses. D Street has 5 houses. And again, at this point, you might be able to predict that F Street has 7 houses. So each type of sublevel, S, P, D, and F, has a different number of orbitals, or a different number of houses that you can put electrons in. And just like you could possibly have more than one person living in one house for that address, you can have up to 2 electrons in each orbital. So each orbital can hold 2 electrons, or each house can have 2 electrons in it. This table is a summary of all the information that we just went over for the address of an electron. Here's our principal energy levels. This was like our town. Then we have our sublevels. This was like our street name. Then we have the number of orbitals. This would be like the house number. Then we have the number of electrons. How many people can you put in each house? In principal energy level 1, there's one street, and its name is S. There's one house on S Street, and you can put 2 electrons in it. In energy level 2, or in city 2, there are 2 streets, S and P. That means there's 4 houses, 1 S house and 3 P houses, or P orbitals, so that's 4 altogether, times 2 electrons each makes 8 electrons. The third principal energy level has S, P, and D streets for a total of 9 orbitals, or 9 houses, and 18 electrons altogether. The fourth principal energy level has 4 sublevels, 16 orbitals, for a total of 32 electrons. And we could go ahead and put the same list for energy levels 5, 6, and 7. You might notice, if you remember from either biology or junior high, you might notice that you've seen these numbers before. When you draw the pictures of the planetary model with the rings, the electrons are in the rings around the outside, these are the numbers that you usually have to memorize: 2, 8, 18, and 32. Okay, now let's go back and talk about the shapes of those atomic orbitals. Remember that those atomic orbitals, S, P, D, and F, represent the houses that we put electrons in, or the areas that they can be found in, and each type of sublevel has its own shapes for its orbitals. So the shapes illustrate the probable locations of electrons in atoms. The first energy level 1, has an S sublevel, and the S sublevels are always shaped like a sphere. The second energy level also has an s sublevel. It would be the same shape, but bigger than the first. And we also know that the second energy level also has a p sublevel. Remember, there were 3 orbitals in the p sublevel, so that means there are 3 shapes here. And this is what they look like on the computer. When you draw them by hand, they kind of look like, this one looks like the infinity symbol. This one looks like the number 8. And this one just kind of looks like a sideways bow tie. Each shape is relatively the same. They're just turned in different directions. And the directions that they're turned correspond to the same directions that you're used to from math. The horizontal direction is the x direction. The vertical direction, which is this one, is the y direction. And then the third direction is the z direction. Z is supposed to come straight out of the page at you. This is like the third or the 3D kind of direction. All of these shapes nest on top of one another. You start with this one in the very center of the atom, and then this one would be like a shell around the outside. I usually compare these to these Russian nesting dolls. How you crack open the biggest one and there's a littler one inside. And then you crack open that one and there's another littler one inside. Atoms are kind of like that. Last week we compared it to Shrek and we said atoms are like onions, they have layers. So the center one would be right in the middle, and then the second one would go right around the outside. These would nest in kind of along with those. The rest of the shapes. Once we get up to energy level 3, we still have an S. It's the same sphere as before, it's just bigger than the other 2. We still have the same 3 shapes for the P sublevel. Again, they're just bigger. And we're also going to learn the shapes for the D sublevel. There are 5 of these shapes, but 4 of them are virtually the same. When you look at the shapes for the D sublevels, 4 of them look like 4-leaf clovers or like flowers. And again, these are just turned in different directions along the coordinate plane. They just face in different directions, but they're all the same shape. And then there's one over here that's kind of weird. It looks like a p orbital with a belt around the center. So there's 4 flowers and then an 8 with a belt. And that's as far as we're going to go. We're not going to learn the shapes for the F sublevels. There's 7 of them that get a little more complicated. So this is good enough for us, knowing the shapes of the D sublevels. Okay, so that's it for the address for the electrons. And next up will be rules for writing down the address for electrons.